Hello my dear students, welcome back to my class. In today's class, we will be starting with a new chapter, that is geometrical optics or ray optics or rectilinear propagation of light. Before starting, we have to discuss what are the properties of light. We know that light is an electromagnetic wave which was proposed by Maxwell. It consists of varying electric and magnetic field, and the electric field oscillates. This is the oscillation of electric field. The magnetic field also oscillates, and the propagation of wave. All the three are perpendicular to each other. Okay, so this diagram shows us that the electric field, the magnetic field, and the direction of propagation are perpendicular to each other. So suppose the electric field is oscillating along the x-axis, the magnetic field is oscillating along the y-axis, then the propagation is along the z-axis. Okay, now if we know the direction of electric field and magnetic field, we also know the direction of propagation of wave. The direction of propagation of wave is always along E cross B. We'll discuss this in details in chapter electromagnetic waves. Okay, the amplitude of electric field oscillation is E naught and the amplitude of magnetic field oscillation is B naught. The speed of light is E naught by B naught. And in a medium, the amplitude of electric field oscillation is E naught m, and the amplitude of magnetic field oscillation is B naught m. M stands for medium. Then the speed of light in medium is E naught m by B naught m. Okay, now here the one more important thing is the electric field oscillation and the magnetic field oscillation are always in same phase. They are always in same phase. That means they reach their maximum together, they reach their zero value or the minimum value together. Okay, they are always in same phase. The electric field and the magnetic field are always in same phase. Okay, then the next property, obviously the speed of light is 3 into 10 raised to power 8 meter per second. In fact, this is the speed of all types of electromagnetic wave. Then frequency, this is very important point. Frequency of a wave depends on the source. So that means suppose a light source is emitting light, okay, any light, then the frequency of that light will depend on that source only. It does not depend on whether light is traveling in one medium or other medium. In every medium its frequency will remain same because it depends on the source was same. Okay, so it does not change when light propagates from one medium to other. The color of the light depends on the frequency. So that is why a color of light will not change when it travels from one medium to other medium because frequency does not change. Okay, but wavelength and hence speed depends on the medium. What do you mean by this? You know that any wave speed is v is equal to lambda into frequency. Similarly, light is an electromagnetic wave, so speed of light is c and lambda into f. C is equal to lambda into f. Any wave, this is valid for any wave. Okay, wave velocity is equal to lambda, that is wavelength, into frequency. So it is valid also for electromagnetic wave. So the speed of light is equal to lambda into frequency. Now lambda changes with medium. So when light will pass from one medium to other medium, its wavelength will change. Its frequency is not changing, but its wavelength is changing. If wavelength is changing, that means speed is changing. Okay, in fact wavelength and hence speed decreases in a medium. Okay, that means wavelength and hence the speed of light are maximum in vacuum. Okay, are maximum in vacuum, and in a medium it decreases. Okay, then there is one more relation that we will derive in electromagnetic waves. C is equal to 1 by under root epsilon naught mu naught. So the speed of light in vacuum is equal to 1 by under root epsilon naught mu naught, where epsilon naught is permittivity of free space and mu naught is permeability of free space. We have discussed in details about what is permittivity and what is permeability. Similarly, the speed of light in medium will be equal to 1 by under root epsilon mu. Now what is epsilon mu? Epsilon is the permittivity in a medium and mu is the permeability in the medium. Okay, next point is when light or any wave transmits from one medium to other. So any wave, this is a general phenomena, for any wave it is valid. So when light or any other wave transmits from one medium to other, so this light is transmitting from here to here, in that case there will be no change in phase. Okay, there will be no change in phase. Okay, we have discussed in what is the meaning of phase in details. The oscillating function y is equal to a sine omega t plus phi, this term inside the sign, this term is called phase. Okay, this term is called phase. So phase does not change when light transmits from one medium to other, but when there is reflection of light, there is two cases. See, when light is reflected from a denser medium. Now what do you mean by denser medium? So a medium is more dense if the speed of light is less, and a medium is rarer compared to other medium if the speed of light is more. So speed more, rarer medium; speed less, denser medium. So when light is getting reflected from a denser medium, that means light is willing to travel, or light wants to travel from rarer to denser medium. So that is why it is getting reflected from a denser medium. So when light gets reflected from a denser medium, there is a phase change of pi. Now what do you mean by pi phase change? See, I'll draw here. Pi phase change means, suppose this is a wave, okay, and this is one more wave, like this I have drawn. Okay, so here you will see that there is a phase change of pi between this wave and this wave. So phase change of pi means when one is at the maximum, other is at the minimum. Okay, so this is the meaning of phase change of pi. That means when light travels from a rarer medium to a denser medium and it is getting reflected at the denser medium interface, in that case the reflected wave will have a phase change of pi. That means if the light came like this, it will go like this. There will be a phase change of pi. But if the light is reflected from a rarer medium, that means the light is traveling from denser medium towards the rarer medium, but it is getting reflected at the interface of the rarer medium, in that case there will be no phase change. So again I'll repeat, when light travels from rarer to denser, in that case there is a phase change of pi, and when light travels from denser to rarer but getting reflected from the rarer medium, in that case there is no phase change. And in transmitted light there is no phase change whether the light travels from rarer to denser medium or denser to rarer medium. Light, just like any other electromagnetic wave, carries energy and momentum, which is given by Planck's law. We have already discussed that in modern physics. Okay, now the next thing is refractive index. Now what is refractive index, which is represented by mu or n? Refractive index is a property of a transparent medium for a given light. Now what do you mean by for a given light? This is very important. See, in vacuum, speed of light of all colors is same. So whether it is red light, whether it is violet light, whether it is blue light, speed of light will be same in vacuum for all the colors. But in medium, the speed of light is different for different colors. Okay, so that is why I have written here, it is a property of a transparent medium for a given light. So for red light, the same medium will have a different refractive index. For blue light, the same medium will have a different refractive index. Okay, so all colors will give a different refractive index for the same medium. Okay, but first what we will define here is the average refractive index. Okay, so you will take the average speed then. So the average refractive index mu is defined as the speed of light in vacuum divided by speed of light in the medium. This is the refractive index of the medium. Okay, so because C is always greater than Cm, you will say mu is always greater than equal to 1. So for any medium, mu will be greater than 1. Okay, so mu can also be written as, see, C is equal to what? Lambda into F. Cm is equal to what? Lambda m into F. This lambda, this wavelength is in vacuum and this wavelength is in medium. Wavelength changes from one medium to other, but frequency does not change. So frequency will be getting cancelled. So from this, sometimes you will require the the wavelength in medium. See, this is the relation between the wavelength of light in a medium with wavelength of light in vacuum and the refractive index of the medium. This is very important. This is the relation between the wavelength of light in medium and wavelength of light in vacuum with refractive index of the medium. Lambda m is equal to lambda by mu. Now, mu is C by Cm. Now C is 1 by under root epsilon naught mu naught. Cm is 1 by under root epsilon mu. From this you will get mu is equal to under root epsilon by epsilon naught into mu by mu naught. Now epsilon by epsilon naught can be written as epsilon r and mu by mu naught can be written as mu r. Okay, so mu is equal to under root epsilon r mu r, where epsilon r is relative permittivity and mu r is relative permeability of the medium. Okay, so mu, again I'll repeat, is equal to, from here epsilon by epsilon naught can be written as epsilon r and mu by mu naught can be written as mu r. So this is the refractive index in terms of permeability of the medium and permittivity of the. Okay, then there is a term called relative refractive index. What is relative refractive index? It is the refractive index of one medium with respect to other. So relative refractive index is defined as the refractive index of one medium with respect to the other. So for example, relative refractive index can be written as mu relative or mu to 1 or 1 mu to. Now what do you mean by mu to 1? Mu to 1 means refractive index of medium 2 with respect to medium 1. Again I'll repeat, the relative refractive index mu to 1 is said as refractive index of medium 2 with respect to medium 1. Sometimes it is also written like this. This means what? Mu 1 mu 2 means what? The refractive index of medium 2 with respect to medium 1. Okay, so the refractive index of medium 2 with respect to medium 1 is equal to mu 2 by 1. Similarly, they can also ask you the refractive index of medium 1 with respect to medium 2. The refractive index of medium 1 with respect to medium 2 is equal to mu 1 by mu 2. That means mu 2 1 is equal to 1 by mu 1 2. Okay, then Cauchy's relation. Till now we have discussed average refractive index. Okay, till now we have discussed average refractive index. Now what we are going to do is we will see how this refractive index varies with color. Okay, because I've told you that the speed of light for different colors in the same medium is different. That means when red light is entering in this medium, the speed is different than the violet light. Okay, but till now we have taken the average speed. That is why we have calculated the average refractive index. Now see, Cauchy, what he did was he found out a relation between the refractive index as a function of wavelength. That means in one medium, different wavelengths will have different refractive index. Okay, so for a given medium, the refractive index of different colors are different. Okay, this is Cauchy's statement for a given medium. So one medium, in one medium, refractive index of different colors are different, and it is given by the Cauchy's relation, that is mu lambda is equal to a plus b by lambda square plus c by lambda power 4 plus dot dot. These higher powers we will neglect and we will only write mu lambda is equal to a plus b by lambda square. Okay, a and b are medium dependent constants. Okay, a, b and obviously c also are medium dependent constants, and lambda is the wavelength of the light. So from here you can see that there is an inverse relation between refractive index and wavelength. More the wavelength, less the refractive index. More the wavelength, less the refractive index. That means the refractive index is maximum for violet light because it has minimum wavelength. Okay, so the refractive index I've written here, refractive index of red light is least and violet light is maximum. Okay, now you know that C is equal to, one more way you can think about it is C is equal to lambda f, right? And mu is equal to C by Cm, right? And C by Cm can also be written as lambda by lambda m. Okay, So from here you can see that refractive index is inversely proportional to the wavelength. Now you know that red light has maximum wavelength, so red light will have minimum. Okay, that is why refractive index of red light is least and violet light is maximum. Okay, now in a medium, red light travels with maximum speed. That is what I have said. So speed of light is maximum for red light and refractive index is minimum for red light. Similarly, speed of light is minimum for violet light and refractive index is maximum for violet light. They are inverse relations. Speed and refractive index have inverse relation because mu is C by Cm. So mu and Cm has inverse relation. All right. Okay. Then next thing is dispersion of light. So what is dispersion of light? See, we know that light of different colors have different refractive index for the same medium. Okay, so what we will do now, see, light of different wavelength or different colors have same speed in vacuum mein to they have same speed, but in medium they have different speeds, so that is why they have different refractive index. Okay, if they have different refractive index, then they will have different bending capacity. This we will study in detail in refraction. Okay, how the light bends when it travels from one medium to other. But because all the colors have different refractive index, that is why they will bend differently. The more the refractive index, more is the bending or more is the deviation. So that is why red light will deviate the least or bend the least, and violet light, which has the maximum mu, will deviate the most. That is why the spectrum always have violet light at the bottom for a single prism and red light at the top. Okay, and why is the light getting splitted? This process of splitting of light is called dispersion. Why is the light getting splitted? Because of this Cauchy's relation that we have studied, because of the speed of light is same in vacuum of all colors but different in a medium. Okay, that is the refractive index is different for different colors in a medium. Okay, so this is the cause of dispersion of light. So the dispersion of light definition is the splitting of white light into component colors, the splitting of white light into component colors. Okay, we will study in details about dispersion of light, okay, in the subsequent lectures. Now these were the properties of light that we have discussed. Now in this chapter we will be mostly dealing with these few topics. First is the reflection of light. Now in reflection of light, what we will discuss? In reflection of light, we will be discussing about the reflection through plane surface, reflection through curved surface, that is the spherical surface. Okay, we'll discuss different formulas, different situations. Then comes the refraction of light. Okay, here also we will discuss refraction through plane surface, refraction through curved surface, okay, and also lens. Then comes dispersion of light, the definition of which we have already discussed. Then we will discuss the scattering of light, and finally the most important thing for JEE mains is optical instruments, where we will be discussing about microscope, telescope, okay, some other optical instruments also. All right, so let's start with the chapter. So what is geometrical optics? The study of geometrical optics is the study of light in which light is considered as moving along a straight line. So we consider the light to be moving in a straight line in this chapter. Okay, a ray of light gives the direction of propagation. So what is a ray? A ray is a imaginary line, okay, which gives you the sense of the direction of propagation. Okay, that means if you give the arrow like this, you will say this light is traveling in this direction. That's it. This is represented by this line called the ray, and a bunch of these rays is called a beam. Okay, now when light meets a surface, so if when light is striking any optical instrument, it can be any surface which separates the two media, so there when light strikes the two surface, okay, or you can say interface of the two surface, right, then there can be reflection, there can be refraction. Okay, so light can transmit or get reflected to back to the same medium. An image or an array of images may be formed due to this. We will discuss what is an object, what is an image, and how images are formed in details in the later part of this chapter. Okay, then there is beam of light. So a bunch of rays is called a beam of light. Now beam can be of three types. The first is the convergent beam of light. Now in a convergent beam of light, you will see that the area of cross section is decreasing. So if the area of cross section is decreasing, in that case you will say that the intensity is increasing, because intensity is energy per unit area per unit time. Now area is decreasing, so intensity will be increasing. In a divergent beam of light, the area increases. So in a divergent beam of light, you will say that the intensity is decreasing. Okay. Then there is a parallel beam of light in which the intensity remains constant and rays are parallel to each other. So area of cross section remains fixed. Okay. Then what is a mirror? Mirror is a highly polished, smooth surface from which most of the incident light gets reflected. It is represented by a line with hatches in reverse side of the smooth surface. So this is the smooth side, this is the silvered side. Okay, silvered side is represented by these hatches, okay, or these lines, right? And mirror is basically a highly polished smooth surface from where almost all lights get reflected, right? Now we are studying the most important definition of this chapter, that is what is object and image. Without knowing what is object and image, we will not be able to continue further in this chapter. If you have not understood properly what is an object and what is an image, this chapter is going to be very, very difficult for you. So everybody listen carefully, what is an object and what is an image. Okay. So first, what is an object? See, an object is a point of intersection of incident rays. Simple. Object is what? Object is not something which you can touch or feel. It's not necessary. The simple definition of object in optics is the point of intersection of incident rays. Wherever the incident rays are intersecting, that point is an object. Okay. So objects can be real or virtual. I'll discuss. Objects can be real or virtual. First we will discuss what is a real object. Okay. See, in a real object there is actual intersection of incident rays. Again I'll repeat, in a real object there is actual intersection of incident rays. So here this is an optical instrument, it can be anything. Okay, this is it can be anything. I have drawn it as a lens here, but it can be anything. Okay, so this is an optical instrument here and this is the object. Now from here you can see that light ray is diverging, okay, or the beam is diverging. It is a divergent beam. Okay, and there is an actual intersection of these rays. Whenever there is an actual intersection of these rays, this point is a real object. From a real object, you must remember, from a real object, rays will always, or incident rays will always diverge. Incident rays will always diverge from real object. Second thing that you have to remember in real object is it is always in front of an optical instrument. This is very important. It is always in front of the optical instrument. Now front does not mean that it has to be in the left side. No, front means that light, so suppose light is going from this side, then this is the front, but suppose light is going like this, then this is the front. Okay, everybody I hope knows the meaning of front and behind, right? So real object is always in front of the interface, right? From here, see, this point is, this is the real object. Okay, this is the real object and this is forming a real image. Now what is real image, I'll discuss in the next definition, but I'm telling you now that I have drawn here the real image. Okay, now real image is formed here, but light ray is still traveling, right? Light ray is traveling. Okay, now what I have done now is I have introduced one more optical instrument here. Now when I have introduced one more optical instrument here, in that case what is happening is this image from the first optical instrument is acting as the object for the second optical instrument. Okay, so point P is image for first lens, but it is object for second lens. Now what comes to our mind is whether this object is real or virtual. Okay, now if you go by the English meaning of object, you will say that this is virtual. Why? Because it is something that you cannot touch or feel. It is behind you. Okay, it is imaginary. It is not something which you can touch or feel. So you'll say that this is virtual object. No, but in geometrical optics, the definition of object is different. Again, I'll tell you what is the definition of real object. First thing is there has to be actual intersection of light. Second thing is rays must diverge. And the third thing is it must be in front of an optical instrument. Any one of these conditions, if it is satisfied, that means all the three conditions will be satisfied. Okay, so here you can clearly see that this object is in front of this optical instrument. That means this is a real object. First. Second, you can clearly see that ray, there is an actual intersection of ray here. Again, that means this object is real. You can also see that rays are diverging from this point. If rays are diverging from this point, that means what? That means again the object is real. Now, what is a virtual object? So in real object, we have seen that there is actual intersection of incident rays. In a virtual object, you will see that there is apparent intersection of incident rays. The rays appears to converge at a point. So I'll show you in this diagram. See, this is the incident ray and this is the optical instrument. Suppose a mirror, and this ray is striking the mirror, but it wants to, or it wanted to intersect at this point, but because it got intercepted by the mirror, so the rays could not move here, right? So the apparent intersection of these two incident rays is the virtual object. Okay, and this virtual object will be forming an image at this point. So again I'll repeat, what is virtual object? Virtual object, there will be apparent intersection of incident rays and the rays will appear to converge. The virtual object is always behind the optical instrument, as you can see from this diagram. So this is the front side because rays are coming from this side, and the virtual object is behind the optical instrument. Okay, so in this diagram again, suppose the optical instrument, this one, the second lens, okay, you put this second lens here instead of here, then what will happen? So I've drawn this diagram here. See, the rays wanted to converge at this point, right? But because it got intercepted by one more optical instrument, so this time what will you say? This point P is a virtual object for the lens 2. Why? Because this rays appears to converge at this point. So again I will repeat, for real object rays always diverge from a point, and for virtual object rays appears to converge at a point. Okay, so you have to be very clear about the definition of real object and virtual object. So I'll read it from here also. See, point from which incident ray actually diverge is called real object here, or point at which rays appears to converge is called virtual object. Object is defined on the basis of incident ray. Very important line. Okay, object is defined on the basis of incident ray. Minimum 2 rays are required to show the position of object. Why? Because intersection point, for intersection point we will need at least 2 rays. Note, an object is called real if it lies on the incident side, otherwise it is virtual. That is what we have said, that front side means real, behind means virtual. Front side means what? It lies on the incident side, and behind means what? It lies opposite to the incident side. Okay. So this was the definition of object. Now what is image? Image is defined as the point of intersection of reflected or refracted rays. So if there is reflection, then there will be intersection of reflected rays, and if there is refraction, then there will be intersection of refracted rays. So for example, here see, this is reflection, okay, and here you will see that the virtual image is formed. So we will first define what is a real and a virtual image. So first, real image. So like object was point of intersection of incident rays, image is point of intersection of reflected or refracted, right? Now first is real image. So in real image there will be actual intersection. There will be actual intersection of reflected or refracted rays. So in real image there will be actual intersection of reflected rays or refracted rays. Okay. Now first is reflected rays. I'll draw a diagram for showing you the real image for a reflected ray. So suppose this is a plane mirror and you have a virtual object like this. So this is a virtual object, and after reflection, ray of light is intersecting at this point. So this is a real image. This is what? A real image. This is a virtual object and a real image. So you will see that whenever there is actual intersection of reflected ray, you will say that the light is converging. So there is converging of light. So when light converges after reflection, then you will say that the image is real. Okay. So actual intersection of reflected rays, here you will say light is converging always. For example, like for real object, light was diverging from the point of real object. But for real image, light is converging at the point of real image. Okay, I'll show you for a lens also. So this is the symbol of a lens. So here again, suppose this is the object, a real object, and this is the actual intersection of refracted rays. This is a real image. Again you will see there is converging of rays. So this is real image from a lens. This is real object. Okay. When real object will be formed, when virtual object will be formed, all the cases we will discuss in details. I am just showing you some examples now. We will discuss all of these cases in details. Okay. Now again I'll repeat, what is real image? Real image, there is actual intersection of reflected or refracted rays. Okay. Now for reflection, you know that there has to be actual intersection, right? So if there is actual intersection, that means in reflection the real image has to be in front. Real image is in front. Why? Because actual intersection can occur only in the front, because light is again reflected back to the same medium. So for reflection, you will say that real image is formed in front of the mirror. Okay, in front of the mirror. And for refraction, because light has now reached the other side or behind, so actual intersection of light after refraction can occur only behind. Okay, so for refraction, real image is behind the optical instrument. Okay. Now real image can be projected on a screen. Real image can be projected on a screen, but virtual image cannot be projected on a screen. Okay. Now what is virtual image? Now the next definition is virtual image. So this is again the point of intersection of reflected or refracted rays, but this time there is apparent intersection. Apparent intersection, or you will say that rays appears to diverge. Rays appears to diverge from this point. Rays appears to diverge from this point. So I'll show you one example of reflection as well as refraction. See, suppose this is a mirror and a real object. Okay. Now, this is a reflection. This is the reflected ray. This is the incident ray. This is the reflected ray. From here also I'll draw one more incident ray and reflected ray. To form an image, we will need minimum 2 rays, because for intersection we need minimum 2 rays, right? So these two reflected rays cannot intersect here. You can see that these two reflected rays cannot intersect here, but it will intersect somewhere behind. Okay. So this point is the virtual image because it is behind the mirror. Virtual image, there is no actual intersection here, and light appears to diverge from this point. You can clearly see that light appears to diverge from this point. Okay, I'll show you one example of refraction also. So suppose you have a lens. Okay, suppose you have a diverging lens. So diverging lens symbol is like this. Okay, we'll discuss the symbols later on also. So this is a diverging lens. Okay, so this is a diverging lens, and suppose this is the object, and light ray after reflection, light ray after refraction, sorry, will diverge, right? So light rays after refraction will diverge. One more ray I can draw like this also. Light passing through optical center of the lens emerge undeviated. We will discuss this also afterwards. Now we are only discussing the definition. You will see that these two are the refracted rays. Now these two refracted rays are not intersecting in this side, they are intersecting virtually here. So this is the image. Okay, so this is a virtual image. Again, you will see that from the point of virtual image, light appears to diverge. Okay, so virtual image is there is apparent intersection, and refracted or reflected rays both appears to diverge from this point of virtual image, right? Virtual image cannot be projected on a screen. It cannot be projected on a screen. Virtual image cannot be projected on a screen. Okay, so this is the definition of virtual image. Now there is one more important thing. A real image can be captured on a screen, that we know already, right? Preferably the surface should be white in color so that we can see the image clearly. So whenever the screen is white in color, we see the image clearly. This image on the screen can be perceived by the eye. Now what about virtual images? You know that virtual image cannot be captured on a screen, right? Since they cannot be captured on a screen, is it possible to see them? Well, from your experience, you know that you can see them, right? In a plane mirror, we have seen that a virtual image is formed, right? In a plane mirror, virtual image is formed, and you are able to see yourself through the plane mirror. So that means you can see the virtual image. How? How is it done? See, there is a lens in our eye and there is a screen in our eye. This lens, what it does is it focuses the diverging set of rays on the retina, forming a real image. So even if there is a virtual image formed, that virtual image acts as an object for the eye lens. Okay, and the eye lens forms a real image of that object on its retina. Retina is the screen. Okay, the screen of the eye is called retina. We will discuss the function of the eye in details later on. Okay, now in a similar manner, a camera can also convert a virtual image into a real image, which is captured on the film. So see here, in a camera, what happens is, whenever a virtual image is formed, the lens in the camera first converts this virtual image into a real image, and then this real image is captured on the film of the camera. Okay, we will discuss again in optical instruments the functioning of a camera. Now, what is reflection of light? Okay, so when light strikes a means a regular boundary, like you can say when light strikes a mirror or a polished surface, okay, some part of this light gets transferred to the same medium, okay, or you can say turns back to the same medium. This phenomena is called reflection of light. Now reflection can be of two types. One is regular reflection and the other is diffused reflection. Now regular reflection is the reflection from a smooth polished surface, okay. What happens in case of a smooth polished surface is light after reflection goes in one direction only, okay. So I'll say here, in this case the reflected light has large intensity in one direction only. In this direction only there is large intensity. In other directions the intensity is very less. Why is this so? Because in a smooth surface or a polished smooth surface, the normal at every point is in same direction. So if the normal is in same direction, in that case the angle of incidence has to be equal to angle of reflection. So in every case the reflected rays are parallel if the incident rays are parallel, okay. But what happens in a diffused reflection is, see, diffuse reflection occurs when the surface is rough. Now when the surface is rough, in that case the normal at every point is different. Every point the normal is different, okay. So if normal is different, then incident rays are parallel to each other, but because normal is different, so reflected rays are at different angles. Now if reflected ray are at different angles or at random angles, in that case what will you say? You will say that the light is diffused in all directions. That means there is intensity in all directions, okay. So when the surface is rough, we do not get a regular behavior of light, although at each point light ray gets reflected irrespective of the overall nature of the surface. Difference is observed because even in a narrow beam of light there are many rays which are reflected from different points of the surface, and every point of the surface has different normals, okay, means normal in different directions, okay. So many rays which are reflected from different points of the surface, and it is quite possible that these rays may move in different directions due to irregularity of the surface. This process enables to see an object from any position. So see, this is very important statement. Suppose you have a book, right? A book can be seen from any direction, okay. Why? Because it is showing diffused reflection, because its surface is rough. That is why it can be seen from any direction, because light from a source when strikes the book, it gets reflected in all directions, and you can see that the reflection of light from that book is entering your eye, okay. But a shiny object will be seen from a definite direction only, because it will reflect light in a definite direction only, okay. Now law of reflection: the incident ray, the reflected ray, and the normal at the point of incidence. So this is the incident ray, this is the reflected ray, and the normal at the point of incidence lie on the same plane. So the first point in law of reflection is the incident ray, the reflected ray, and the normal are lying on the same point or same plane, sorry, okay. That means this light after reflection cannot go here, it will always lie in the same plane, okay. Now that means you can say that incident ray, the normal, and the reflected ray are coplanar, okay. Now you have studied in vectors that the condition of coplanarity is that the scalar triple product has to be 0. See, this is suppose a vector in the direction of incident ray, this is the vector in the direction of normal, and this is the vector in the direction of reflected ray. You know that all the three vectors are coplanar. So that means A cross B, or you can say I cross n dot r, has to be 0. Why? Because I cross n is perpendicular to the plane, and the perpendicular to the plane and dot product, so that means this vector is perpendicular to the plane and this vector is in the plane, okay. That means the angle between this and this is 90°. So that means the dot product will be 0. So that is why scalar triple product has to be 0. So cross product of two vectors will be 0, okay, when you take the dot product with the third vector. So from here you will see that r dot I cross n is 0, n dot I cross r is 0, or I dot n cross r is 0. Okay, where I is the vector along the incident ray, n is the vector along the normal, and r is the vector along the reflected ray. Okay, then the next point is very important here. The angle of incidence has to be equal to the angle of reflection. The angle of incidence is measured from the normal. Okay, similarly the angle of reflection has to be measured from the normal. Okay, now one more important term here is the angle of deviation. Angle of deviation is represented by delta, and angle of deviation is defined as the angle between the incident ray and the emergent ray. Okay, in case of reflection, the emergent ray is this. Okay, angle between incident ray and emergent ray is called the angle of deviation. It is a general definition, it is not only for reflection. Angle between incident ray and the final emergent ray from any body is called the angle of deviation. So here the light is getting reflected, right? So if the light is getting reflected, I will say that, so if you remember, like you have studied in vectors that the angle between two vectors, if you want to find the angle between two vectors, you have to join it tail to tail, right? So here this is the incident ray vector and this is the reflected ray vector. So what I will do is I will shift this, I will parallelly shift this incident ray vector here. Okay, then this incident ray vector and reflected ray vector will be joined tail to tail, and this angle will be the angle of deviation. Now this is I, this is also I, because angle of incidence is equal to angle of reflection. So this total angle is 180 degree or pi, right? So delta will be pi minus 2i. So angle of deviation is pi minus 2i. Sometimes we also take the larger of the two angles. In that case, deviation can be written as pi plus 2i. So in case you have a more than one option correct question, then you will have to check whether they have given the answer in terms of pi minus 2i or pi plus 2i. Both will be correct. Okay, because in deviation, angle of deviation definition, they have not mentioned anything about which angle you have to take. So both angles you can take, the smaller of the two angle form or the larger of the two angle form. Okay, now angle of deviation versus the angle of incidence graph, if you draw, you can see here this is a straight line with negative slope, right, and positive y-intercept. So positive y-intercept, that is pi or 180 degree, and the slope is minus 2. When I becomes 90 degree, the deviation becomes 0. When I becomes 0, I becomes 0 means normal incidence. Okay, normal incidence deviation is maximum. Why? Because light will retrace its path. So I've written it here also. Special cases. First is the normal incidence. Normal incidence means I is 0. When I is 0, deviation is 180 degree. So this is normal incidence. When light is incident normally, light retraces its path. Then the second thing is grazing incidence. Grazing incidence means light is incident at an angle 90 degree. So when light is incident at an angle 90 degree, in that case there is no deviation. Okay. So in case of reflection of light, magnitude of velocity of light remains unchanged. Why? Because reflection may light is moving back to the same medium. So in one medium the speed will be constant, right? Okay, but when there is grazing incidence, you will say speed is constant, also velocity is constant. Okay, also velocity is constant. Now we will discuss law of reflection in vector form. So law of reflection in vector form. Suppose E1 cap is a unit vector along incident ray. So this is E1 cap, which is a unit vector along incident ray. N cap is a unit vector along normal, and E2 cap is a unit vector along the reflected ray. Okay, now let us resolve the E1 cap vector into two components. One is parallel to the surface and the other is along the normal or the perpendicular to the surface. So E1 cap can be written as E1 parallel vector plus E1 perpendicular vector. Okay, E1 cap can be written as E1 parallel plus E1 perpendicular. Okay, now here E2 cap can be written as, see, you know that in reflected ray only the component of ray which is perpendicular to the surface gets reversed along the, means the component of the ray which is along the surface remains unchanged. So that means if this is E1 parallel, then this will also be E1 parallel, and if this is E1 perpendicular, this will be minus E1 perpendicular. So that means E2 cap can be written as E1 parallel vector minus E1 perpendicular vector, because E2 cap is the resultant of E1 parallel vector and minus E1 perpendicular vector. Okay, so we have got the value of E2 cap. Okay, now let us do the dot product of E1 cap and N cap. Okay, E1 cap dot N cap can be written as E1 vector can be written as E1 parallel vector. Sorry, E1 cap can be written as E1 parallel vector plus E1 perpendicular vector dot N cap. Okay, this is not a unit vector. Okay, the components are not unit vector. The resultant of this two is a unit vector. All right. So now here E1 parallel plus E1 perpendicular dot N cap can be written as E1 parallel dot N cap is 0. Why? Because N cap is in this direction and parallel vector E1 parallel is in this direction. So that means they are perpendicular to each other. So the dot product will be 0, right? So the dot product is 0, this two. But this one E1 perpendicular dot N cap can be written as A dot B is AB cos theta, right? A. The magnitude of E1 perpendicular is E1 perpendicular. Magnitude of N cap is 1 because it is a unit vector, and because the angle between these two is 0 degree. Why? Because N cap is in this direction, even perpendicular is also in this direction. So you will say cos 0. So you will get E1 cap dot N cap is equal to E1 perpendicular because cos 0 is 1. Okay. Now E2 cap we know is E1 parallel minus E1 perpendicular from here. E2 cap is E1 parallel minus E1 perpendicular. But minus E1 perpendicular can be written as plus E1 perpendicular minus 2 E1 perpendicular. Okay, why we have written it like this? Because E1 parallel plus E1 perpendicular, E1 parallel plus E1 perpendicular is E1 cap. So that means this two addition can be written as E1 cap. Okay, so E2 cap will be equal to E1 cap minus 2 E1 perpendicular. Okay, now you also know that any vector can be written as the magnitude of that vector multiplied by the unit vector in that direction. Okay, right? So here E1 perpendicular vector can be written as E1 perpendicular multiplied by the unit vector in this direction. Now unit vector in this direction is N cap. In the direction of E1 perpendicular, in the direction of E1 perpendicular, the unit vector is N cap, right? So you can write minus 2 E1 perpendicular vector as minus 2 E1 perpendicular into N cap. So from this you will get E2 cap is equal to E1 cap minus, listen carefully now, E1 perpendicular can be written as E1 cap dot N cap from here. Okay, so E1 perpendicular can be written as E1 cap dot N cap. So from this you will get E2 cap is equal to E1 cap minus 2 E1 cap dot N cap into N cap. Okay, take a pause here to learn this formula. This is the law of reflection in vector form. E2 cap is equal to E1 cap minus 2 E1 cap dot N cap into N cap. Okay, so this is the law of reflection in vector form. So suppose in the question they have given you a unit vector along the incident ray and they have given you a unit vector along the normal. That means they have given you the unit vector along reflected. Okay, or they can ask you the unit vector along reflected. All right. Okay, now this is the law of reflection in vector form. We will use this in some questions. For example, here prove that when incident ray suffers two successive reflection from two mutually perpendicular mirrors. So this is two mutually perpendicular mirrors. The first mirror surface is along the x-axis and the second mirror surface is along the y-axis. Then from law of reflection show that the emergent ray is anti-parallel to the incident ray. So if this is the incident ray, you have to show that the emergent ray is anti-parallel to the incident ray. Alright. So what we will do here, see, this is the incident ray, that is E1 cap, and this is the reflected ray, that is E2 cap. So you can say E2 cap is E1 cap minus 2. Now the normal vector here is J cap, right? So you know this formula now. E2 cap is equal to E1 cap minus 2 E1 cap dot N cap into N cap, right? So we are using this here. Now E2 cap is equal to E1 cap minus 2 E1 cap dot N cap can be written as J cap into J cap. Okay. Similarly, E3 cap can be written as E2 cap minus 2 E2 cap dot. So this time the normal in this surface, the normal is along the I cap. Okay. So minus 2 E2 cap dot I cap into I cap. Okay. When you replace this E1 cap, when you replace this E2 cap here, okay, with this, you will get E3 cap is equal to minus E1 cap. So I am asking you here to eliminate E2 cap. Once you eliminate E2 cap, you will get E3 cap is equal to minus E1 cap. Okay. You have to solve this yourself. It is very simple. You just have to put the value of E2 cap here and the value of E2 cap here. From this equation, you will get this result. So E3 cap is equal to minus E1 cap means what? Means this vector is anti-parallel to this vector. Okay. But there is one more method. There is one more method to understand this. See, that is what more simpler method. You know that in a reflected ray, the normal component gets reversed and the parallel component remains same, right? So here, if this is E1 cap, or you can say if this is the vector xi cap plus yj cap, then this vector will be, see, the normal is along j cap, right? The normal is along j cap and the component along normal gets reversed and the component along the mirror, or parallel to the mirror remains same. So this will remain same. So I'll write xi cap minus yj cap, this one. But now the normal is along the x-axis. So this time x component will get reversed. So here you will write minus xi cap minus yj cap. This will get reversed. This will remain same. Okay. So from here also you can see that this is xi cap plus yj cap and this is minus xi cap plus minus yj cap. Okay. From here again these two vectors are anti-parallel. So whenever incident ray suffers two successive reflection from two mutually perpendicular mirrors, the final ray is anti-parallel to the original ray. Okay. So here also I have written E1 cap is AI cap plus BJ cap, or you can say XI cap plus YJ cap. E2 cap is AI cap minus BJ cap and E3 cap is minus AI cap minus BJ cap. So from this two you will see E1 is anti-parallel to E3. Okay, here I have used xi cap plus yj cap. You can also use ai cap plus bj cap, whatever you want to use, or you can prove it using the law of vector, means law of reflection in vector form. Okay. Now suppose you have two plane mirrors which are at an angle theta. Now this is very important. Everybody have to listen to this carefully. So we have two plane mirrors which are inclined at an angle theta. Okay, a ray of light is incident on the first mirror and it gets reflected and then strikes the second mirror. Okay, again it gets reflected. So after two reflection, we need to find the deviation. So this is the incident ray, this is the emergent ray after two reflections. So we need to find the angle between the incident ray and the emergent ray. Now to find the angle between incident ray and emergent ray, you know that the two vectors, if you want to find the angle between two vectors, what you have to do is you have to join it tail to tail. So if this is the emergent ray, this is the incident ray, this has to be the angle of deviation. Okay. So this is the angle of deviation. Now how to find this? Suppose the incident ray here is alpha. This is the normal to this mirror. So this angle will also be alpha because angle of incidence is equal to angle of reflection. Right. Now if this angle is alpha, obviously this angle is 90 minus alpha. Right. Similarly, let us say that this angle is beta. In that case, this angle is also beta. Right. So if this is beta, this is 90 minus beta. but this forms a triangle. So theta plus 90 minus alpha plus 90 minus beta has to be equal to 180 degree, because sum of all the angles of a triangle is 180 degree. From this you are getting alpha plus beta is equal to theta. Now once you have got this, in this triangle what you can see? In this triangle you can see that this angle is 2 alpha and this angle is 2 beta, right? This angle is 2 alpha, this angle is 2 beta. Now you know that this is an exterior angle in this triangle, and exterior angle is equal to the sum of two remote interior angles. That means delta is equal to 2 alpha plus 2 beta, that is 2 into alpha plus beta, but alpha plus beta is theta, that means the angle of deviation is 2 theta. So the angle of deviation that will come out is either 2 theta or pi minus 2 theta. There is a very important note here. You can see that the angle of deviation has come out to be independent of alpha or beta. That means angle of deviation is independent of the angle of incidence. So angle of deviation after two successive reflection will depend only on the angle between the two mirrors. Okay, but there is one more thing here that you have to think about when you draw the ray diagram. See, here I have drawn this ray and I have taken the normal this side, but is it not possible that the ray after striking here, the normal is in this direction? It is possible, right? And then the light ray will get reflected in this direction. Okay, so how to know when you have to take the normal in this direction, or that means when the reflected ray will be in this direction and when the reflected ray will be in this direction. Okay, so let us see. Suppose that this is the incident ray at an angle alpha, this is the reflected ray. Okay, and suppose the reflection from the second mirror is in this direction, that means the normal is here. Okay, now let us say that this whole angle here, this whole angle from the reflected ray is suppose x. Okay, so this is x. All right, then in this triangle you will say that x plus theta plus 90 minus alpha is 180 degree, because this whole triangle, this is 90 minus alpha, this is theta, and this whole angle is x. This x is with the incident ray. Okay, x is with the incident ray, this angle. From this you will get x is equal to 90 minus theta plus alpha. So from this, when you solve this, you will say that x is equal to 90 minus theta plus alpha. All right, now here, so here according to this diagram, this was the incident ray, this was x, right? This was x. Now see, if x is greater than 90, if x is greater than 90, that means the reflection has to be in this side, because if x is greater than 90, that means the normal is means in front. Okay, but if x is less than 90, see here in this case x was less than 90, then the normal was to the right. Okay, so if x is less than 90, then you will say that this case will occur, and if x is greater than 90, then in that case this case will occur. So you know that x is 90 minus theta plus alpha, so you will write 90 minus theta plus alpha is greater than 90, 90 cancelled, that means alpha is greater than theta. So when alpha is greater than theta, then diagram 2, this second diagram, this one, and if alpha is less than theta, then you will draw the diagram 1. So I have told you how the incident ray, the angle means how the angle of incidence is related to the angle between the two mirrors. If alpha is greater than theta, in that case you have to draw this diagram, and if alpha is less than theta, in that case you have to draw this diagram. Okay, so if you remember this, you will save a lot of time while drawing the ray diagram. Okay, so in this class we will study only up to this. Tomorrow we will be studying about the image formation due to plane mirrors. Okay, so we'll complete everything about plane mirror in the next class. Till then, bye bye everybody, take care. I hope you are liking my video. Please like, share and subscribe to my channel.